Well, thank you so much. And thanks to everyone for the opportunity to be here. I'm really excited to talk about some of this stuff. So I want to begin with two graphs, because I think that the moment that we find ourselves in can reasonably well be summarized by these two graphs. So on the first here, we have the results of the ImageNet competition in object classification. And of course, you can see the dramatic elbow of progress that happens around 2012 and with the so-called AlexNet. And this stands in, of course, for the entire deep learning revolution that we're now a part of, and more broadly for just the data science and machine learning revolution that's been happening in the last 10 years. On the right, we have a different graph, which is the number of US states that are using statistical and ML parole prediction instruments across the 20th century. And you can see that even though these methods have a surprisingly long history, they go all the way back to the 1920s and 30s, there is really kind of a step change, this discontinuity that happens around the turn of the millennium. And you can imagine what the most recent 20 years of data look like here. And this, I think, charts the equally stunning, but sometimes less sexy, less celebrated progress of data science and machine learning, not necessarily in terms of its raw capacity, but in terms of the permeation that it has made within society, that it's not only in industry, but it's also in government. It's becoming part of the decision-making apparatus of the world, broadly speaking. And this leap forward in capability, this slow kind of inexorable permeation throughout society, the combination of these two things has made a lot of people concerned. And in particular, that concern has manifested in two distinct communities. There is the community of people who are thinking about kind of present day systems from an ethics and fairness and bias perspective. And then there are also people who are thinking a few years ahead and wondering questions about actual physical safety, whether it's self-driving cars being safe, for use on the roads, or even further out, people asking these questions about existential risk. Right? Might there be a truly dramatic danger that lies for us as these systems increase in their capabilities? And it started to occur to me several years ago that in a way that these two communities, even though they feel very distinct, are actually fundamentally united and fundamentally addressing the same problem. And this problem was, I would say, first very clearly articulated by the MIT cyberneticist Norbert Wiener in 1960. Wiener writes, "We all know the fable of the sorcerer's apprentice. The boy animates the broom to carry water and ends up almost drowning himself. Disastrous results are to be expected not merely in the world of fairy tales, but in the real world. If we use to achieve our purposes a mechanical agency with whose operation we cannot interfere once we have started it, then we had better be quite sure that the purpose put into the machine is the purpose which we really desire, and not merely a colorful imitation of it." Today, this is known as the alignment problem. And the basic idea is, are our systems, are our models learning what we think they're learning? Are we incentivizing the behavior that we think we're incentivizing? Are we making the predictions that we really think we're making? And so this idea of the alignment problem, I think, signals this broader movement that's now happening across these different communities. So I embarked on a 4-year-long quest to try to really tell this story, to learn the history, the historical roots of some of these ideas, to meet the community of people that are engaged in confronting the alignment problem head on a number of fronts. I wanted to chart the incredible growth of this area within just the last 5 years, and its early but I think significant progress, as well as this huge frontier of open problems that remains. Some of these open problems are purely technical, but most of them are deeply interdisciplinary. And so this project became the book, The Alignment Problem, Machine Learning and Human Values, which just came out in the States and will be coming out in the UK in January. So for the next approximately 25 minutes, I'd like to share a bit about what I found. And in particular, because there's way too much to distill into a single conversation, what I want to highlight are the points of connection between the present day concerns of the community around fairness, bias, transparency, the points of connection between that work and the longer term work on technical AI safety and even existential risk. So as a place to begin, I think the natural place to begin when thinking about something like the alignment problem, are these models that we're building really learning what we think they're learning? I think the natural place to start is to look at the training data. So this is the software developer, web developer, Jackie Alcione. And in 2015, he was really excited because Google Photos had just rolled out a brand new version of their system that included these deep convolutional neural networks that were going to be doing automatic photo classification and categorization and so forth. And so when he opened up his browser, this is what he saw. And this example might be familiar to many of us in the data science machine learning community, but it had created an album of pictures of himself and his friend and labeled it gorillas. So this was just pretty much the nightmare scenario. And this particular example is not the only one, unfortunately, but has kind of kicked off this entire movement, as well as technical literature on figuring out what goes wrong in cases like this and what can we do about it. And here I want to highlight the work of MIT's Joy Buolamwini and Google Brain's Timnit Gebru, who have done a lot of really, I think, pioneering work on trying to analyze the nature of the data sets that go into modern face recognition, object classification data sets. And often those training data sets are extremely skewed relative to the population of people that's actually using the system. And they've shown, for example, using the 6 types of the Fitzpatrick skin tone scale, that looking at modern, this was from the end of 2017, I believe that they did this work, kind of then contemporary commercial large scale face identification classification systems. You can see here that the error rates are something like almost tenfold for the people with the darkest skin tone relative to the people with the lightest skin tone. And a big part of why that is the manner in which the training data are collected. And in particular, many of these training data sets were collected by scraping news articles. And so the media bias translates directly into classification disparate error rates. So one kind of well-publicized example of this is the labeled faces in the wild data set, which we might talk about in a moment. But there are subtler cases as well. So I'm thinking about the work of Bean Kim, who is at Google Brain, and she's using these kind of transparency methods. She has a method she's developed with her colleagues called concept activation vectors that shows kind of what concepts appear to be intrinsic to a network's classification of a kind of image. And she showed, for example, that the concept of red in a number of Google's vision models, the concept of red was very intrinsic to the category of a fire truck. Okay, so that makes sense if you're deploying your model in the United States, where fire trucks are almost always red. Makes sense if you're deploying your models in the United Kingdom, where fire trucks are very often red. But it doesn't make sense if you're deploying your model in Australia, where fire trucks are often white, or in the case of Canberra, neon yellow. And so I think there's some promise that transparency methods like this are going to enable us to catch more of these things before they become kind of catastrophic errors in deployment. And we're starting to see also, I think, a real shift in the way that people who curate data sets think about how those data sets may or may not represent a broader community. So as I mentioned, there's the labeled faces in the wild data set. And when it was first published in 2007, there was this note in the peer review paper. It said, the set has its own biases. For example, there are not many images which occur under poor lighting conditions, ... However, the diversity of pictures present is very large. I think this is just very interesting as a little historical note that by the late 2000s, concepts like bias and diversity were being used in these data sets, but they were being used in a very particular way. They were being used to talk about the lighting, the pose, the resolution. By 2019, now the same data set appears with this other disclaimer that is very different, that talks about, okay, there are no children, there are no babies, there are very few elderly people, there are a very small representation of minority groups, et cetera. And in fact, I think one of the most striking things about this data set is in part because it was collected through news articles in the late 2000s, it features the people who would have been in the news in the late 2000s. And so the individual who appears more than any other in the data set is then US President George W. Bush. And in fact, subsequent analysis has shown that there are 2 times as many pictures of George W. Bush as there are of all Black women combined. And so now this data set appears with this giant, red disclaimer. So I think it's more and more people are thinking about this question of does the training data fundamentally actually represent what we want this model to do or how we want this model to be used. And I think one of the things that's really important here is to think about not just this kind of demographic question, but also the temporal question. So here's Princeton University computer scientist Arvind Narayanan, who writes, contrary to the tech moves too fast for society to keep up cliche, in the banking sector, in aviation, there are systems that have been, COBOL systems that have been running since the 70s and 80s that are still in use. So this idea that machine learning models being trained today might still be around for, 50 years from now is kind of terrifying. One of my favorite anecdotes in this space was a group of computational linguists who were trying to replicate a model that they had seen in a paper. And for some reason, they just, no matter what they tried, they couldn't get the accuracy of the paper that they were trying to reproduce. And they thought maybe there was a bug in their code. Maybe this group had some kind of secret sauce that they didn't disclose in the paper, what was going on. And in fact, gradually over time, their model performance started getting worse and worse. And they were trying to figure out what it was. Suddenly they had this insight, which was that they were training the model based on corpora of text that was being scraped off the web. The original paper was from 2016, and they were training a model using the internet of 2017 and the internet of 2018. And it was simply the case that English was changing. The way people were using the language, what people were talking about was just gradually mutating as the culture shifted. And so naturally, these models, if you try them on a test set of a corpus from 2016, are just going to get worse and worse and worse. So I think it's really important to be thinking about this question as well. And I think these timescales can apply not only at the scale of years, but also at the scale of even days. So I was talking with an engineer at a tech company that will remain nameless that was talking to me about they deployed a new version of their ad model, and suddenly their ad revenue started going way down, and they were trying to figure out what was going on. And to make a long story short, they were including the operating system version number and the app version number as a feature into their machine learning model. And the model initially began to learn the concept basically of an early adopter. It said, oh, people who are like the first with this new operating system have kind of this very specific set of interests. They're these types of people, they're into these types of things. But that model got less and less accurate with every passing day, right? Over time, 6 months out, they're not the early adopters anymore. And of course, the model was learning this, but it was always trailing behind. Every day it would learn, but it would still be slightly wrong the following day. And so I think there's a real lesson here that this isn't just a kind of build it once and set it and forget it kind of thing, but that there really is a constant vigilance to make sure that the data that goes into our models really does reflect the world. And the world, of course, is always changing. So there's more things going on here. I mean, even just in this Google Photos Gorillas example than just the training data. So we'll touch back on that in a moment. But I want to highlight here a connection between some of this work, which you might think of as in the kind of contemporary bias space, and this longer term question of AI safety. So there's this idea, this is OpenAI safety team lead Dario Amodei, who published this seminal paper in 2016 called Concrete Problems in AI Safety. One of the problems that they highlighted was what they call robustness to distributional shift or distributional change. And this is a very kind of broad problem within data science and machine learning, particularly in reinforcement learning, but it sort of comes up all over the place, which is, you're trained on a certain kind of distribution. You go out into the world and you start doing things and you start to see things that look different. And ideally, we would want to not only have, human teams thinking very deeply about the training data that goes into these systems, but we might hope for something at least partly automated as well, where the system can itself identify that it's operating out of its training distribution, something's going weird, and it can either defer to a human supervisor or just sort of back off. And so there's a really interesting intersection of quantifying uncertainty. So in the case of robotics or self-driving cars, if you can quantify the measure of uncertainty that your collision model has, let's say, if that uncertainty starts going up, you are entering something that doesn't look like the distribution you were trained on, and you should probably, all things being equal, just slow down. So there's a lot of work that's happening here on this idea of distributional shift and broadly speaking, models that know when they don't know. And you might have wanted that, for example, from the Google Photos system, that perhaps at the time, people were overlooking, there was this gap in the training data, but you'd still have wanted the system to catch that and say, I'm operating on fewer training data than I thought I might be. This doesn't really look as familiar to me as I would be comfortable with, so I'm not going to label it at all. So I think there's a lot of connections that are happening between this kind of longer term safety question and these practical things that are coming up every day. Okay, the second thing, of course, that we want to think about when we're thinking about, are these systems doing what we really want? Is the purpose that we've put into them really, the intent that we have? Does that really become the objective of the system? So the other thing, aside from the training data, is, of course, what's the objective function? And this is something that has really come to a head, I would say, in the last few years through, in large part, the work of Julia Angwin, who is an investigative journalist at ProPublica and more recently at The Markup, who published this article. I think many people will be familiar with it, but it was kind of an expose of criminal risk assessment tools, particularly in the United States, where they are widely used in many areas, including probation, parole, and especially pre-trial detention. So if someone is arrested and their trial date is set, there's this prediction made of how risky is this person, and should we hold them in jail pending their trial, or should we release them pending their trial? And her team did an investigation and noticed what appeared to be a number of racial disparities, striking racial disparities in the way that these scores were being applied. And this really began a broad question that involved not just journalists, not just lawyers, but also the theoretical computer science community into the question of, well, how might you operationalize the concept of fairness, and which quantitative definition should we use? There are people here that have done a lot of really important work. For example, UC Berkeley's Moritz Hart, who has looked at this question of, group calibration. Broadly speaking, calibration is, if you are assigned a risk score of 8 out of 10, you have the same probability to be rearrested as you do if you're white as if you're black. And that has been a very kind of cornerstone metric that's been used within criminology. And then more recently, people are thinking about other metrics, for example, this idea of equalized odds or equalized opportunity, which broadly speaking is saying, for the people who are miscategorized by this classifier, do they have approximately the same chance of being misclassified? Are they equally likely to be rated as too risky versus not risky enough? And importantly, there's been a lot of work in the theoretical computer science community by John Kleinberg, his collaborators at Cornell, Alex Choldachova, her collaborators at Carnegie Mellon, Sam Corbett Davies, his collaborators at Stanford, all sort of converging on this same answer, which is unfortunately, in most cases, you simply cannot satisfy those definitions of fairness simultaneously. And so we have this very complicated policy decision to make, which is we have these ideas articulated in the law about being fair to people, not discriminating, et cetera. But there is a very non-obvious way that gets translated into math. And there are limits to which properties we can hold at the same time. But I think and so I think that's really an important conversation that's now happening kind of at the intersection of law, ethics, and computer science around how we operationalize some of these ideas that exist in the law. But I think there's arguably an even more fundamental issue that's happening here in the criminal justice space, which is, are we really measuring what we think we're measuring? And are we really predicting what we think we're predicting? So for example, it's often said that these models are designed to predict reoffense, to predict crime. But that's not actually, we can't measure crime. We can only measure whether someone was rearrested and reconvicted. And these things are often significantly different. This is a controversy which goes back all the way to the 1930s. The first use of risk assessment models in the United States was in the state of Illinois. And there was this prominent conservative politician complaining, and he writes, because a parolee isn't caught, he is listed as having made good. And so I think it's very interesting that nowadays you're much more likely to see the critique made from the progressives that are saying, because someone is wrongfully arrested, wrongfully convicted, they're getting tagged into the system as having reoffended when they actually didn't. And this is the conservative side of that argument. And they're really two sides of the same coin. And they're getting at this issue that, there's this fundamental gap between what we can actually measure, what we can actually train on, and the thing that we really, at the end of the day, care about. So likewise, there's this question in a number of domains of, are we measuring truth or are we measuring consensus? And in the image recognition domain, this is Andrej Karpathy, who is these days the head of AI at Tesla. But back in his graduate school days, he decided to make himself the human benchmark for the ImageNet competition. So this question of, how do these models do when compared against a human trying to decide, is what breed of dog, a particular picture is, and so forth. And he writes about this experience, what I learned from competing against convets on ImageNet. And one of the points that he makes that I think is really salient is this idea that it's really hard to get 100% quote unquote accuracy on the ImageNet data set because, accuracy with respect to what? The data set labels come from Mechanical Turk. And so if most people thought something was a terrier when it was some other kind of breed of dog, well, whatever people said it was is what the label is. So even if it's not actually a terrier, accuracy depends on matching not the truth, but the consensus. And I think this is, again, just a reminder that what we take of as ground truth in our model is often not. And Kate Crawford of Microsoft Research and AI Now Institute and her collaborators have also pointed out that there are a lot of subjective categories in ImageNet which seem quite strange. For example, one of them is failure or loser. And so what does it mean? And people on Mechanical Turk would go and identify images that look like losers. But what does it actually mean to train a classifier on this data set? This really just represents people's stereotypes, et cetera. So back to the criminal domain, there's a very crucial distinction here around the idea of objective between what we're really predicting. So there are different types of risk that might make someone detained pending their trial. One of them is the risk of committing a crime. The other is the risk of failing to appear. And these things are very different for a number of reasons. For one, if you fail to appear, this is a perfectly observable phenomenon. So 100% of the time, if you're supposed to be in court and you're not there, the court knows about it, basically by definition. But as we were discussing, crime is much more complicated. So particular non-violent crime in the US, in Manhattan, Black and white people self-report that they use marijuana at about the same rate. But a Black Manhattanite is 15 times more likely to be arrested for using marijuana than a white person is. And so we might have this hunch that our models are more trustworthy when they're predicting failure to reappear, which is a perfectly observed variable, than when they're predicting nonviolent crime, which is this highly imperfectly observed variable. And so you're starting to see groups advocating that some of these predictions can be disentangled, and we might trust the failure to reappear prediction, but not trust the crime prediction. One of the things that I think is very striking in this area is this question of what is the model predicting versus how is the model being used. So a lot of these models are predicting the risk that someone will commit a crime or be rearrested rather, while they are awaiting their trial. And these models are explicitly designed and explicitly stated not to be used during sentencing, but sometimes they're used during sentencing anyway. And so I think about, in data science, machine learning, we need something equivalent to what you have in medicine, right? Like on the side of a medicine bottle, it says, use this only as directed, right? And I think we need something increasingly like that for our models as well. If it's a pretrial detention model, not to be used for sentencing, and it should not be used for sentencing. Again, I think there are important distinctions to be made here in whether we are predicting someone's risk or someone's needs. And likewise, what is the intervention that this prediction is going to support? So for example, there's a lot of evidence that, if people have a lot of kids, if they're working multiple jobs, they're less likely to appear for their court date because it's harder for them to get childcare, or it's harder for them to get out of work. Is that a risk or is that a need? And I think this starts to become a very significant question. There's a growing body of research showing that for many people, if you simply remind them of their court appointment, they're way more likely to show up. And so what do you do with this risk assessment that says they have a risk of failing to reappear? Well, there are many different things you can do with that same prediction, right? You can incarcerate the person, or you can send them an SMS the morning of. And I think that conversation is maybe sort of underemphasized. That you have the model on the one hand, but how the model actually supports intervention in the real world is a separate question. And there are many cases like this. For example, in Chicago, there's a predictive policing project that was trying to predict which people would be victims of violent crime. And they were able to identify a list of about 1,000 people, I think, several hundred people, that was at, I think, 100x the normal risk of being victims of homicide. And it turns out that this prediction was largely accurate, but no one could figure out like what to actually do. You've identified this community. What do you do? Do you send police officers to their house, tell them to like be careful? What do you do? And so I think this is really an important question for all of us to have in mind is, you have this prediction, but the prediction needs to support action. So what is that action actually supposed to be? There are a lot of really subtle questions here that end up being pretty significant in terms of actually formulating the objective function, the loss function of your system. So this takes us back to this Google Photos gorilla example. So a lot of image classification systems are trained with what's called cross entropy loss, as I'm sure many of you know. And so here I've just taken the 10 object categories from the CFAR 10 data set as an example. right? And so if you categorize anything as itself, then you have a loss of 0. Otherwise, you have a loss of 1. And this is a uniform loss matrix. So you have the same loss for miscategorizing anything, any x as any y, regardless of the values of x and y. But that doesn't really fit our intuition. In the Google Photos case, what we see is there are particular miscategorizations that might have like a million x the harm, right? And so there's work being done now in the sort of technical AI safety community on this idea of how might we actually try to learn the loss matrix from people by presenting them with different options and saying which of these would be worse. And so I think there's a really interesting frontier here in machine learning of trying to learn this loss function rather than being given it. And so we'll come back to this idea in a second. Before I wrap up, I want to touch on reinforcement learning because we've been mostly talking about supervised learning, but what about RL? So we've seen, of course, that RL is increasingly capable at things like Atari, Go, robotics, self-driving cars. It's also being increasingly used in industry in ways that I think are flying under the radar for some people. So Facebook has talked about very openly about how they're moving from a supervised learning model of their newsfeed, of their app notifications, to a reinforcement learning model. In fact, they're actually using DQN, Deep Q networks, which is exactly the same model that DeepMind was using on Atari, in order to predict how their actions will affect not just your immediate click on that item, but your long-term engagement with the system. And for me, this is very ironic in a way because we've become accustomed to this catchphrase about social media that, you know, you're not the customer, you're the product, that sort of thing. Thinking about the idea that the newsfeed has this DQN algorithm behind it makes me want to propose this alternative formulation of, you know, if you're not the Atari player, you're the Atari game, right? So it is this DQN agent that is learning to play you. But in reinforcement learning, there is this critical question of what is the reward function that we're trying to optimize? And this is extremely subtle, right? In some games, it might be points. In a board game, it might be the maximum probability of winning, et cetera, et cetera. But often the reward is actually quite hard to state, and it's quite hard to get right. So this is a famous example from OpenAI, where they were training a boat, an agent to play this boat racing game, and they were just optimizing for the score. But they found that actually the score and participating in the race become totally uncorrelated in this particular map, where you can just kind of spin around infinitely in this little harbor and pick up points forever. Meanwhile, you know, the race moves on and you're just stuck there. And so you can, this is also kind of an example of distribution shift, that points correlated with winning the race in, you know, 10 out of 11 of the training environments, but in this 11th one, you know, they got totally unglued. There's also this problem in other environments of sparse rewards. This is the notoriously difficult video game Montezuma's Revenge, where you basically have to do, you know, this long sequence of things, each of which is sort of death-defying in order to reach that initial key, which gives you your first points. So the moral here is merely identifying a reward function is not sufficient to make something that's learnable. So how do people confront this problem, where they often add these little incentives, what are called shaping rewards? But these shaping rewards can often go very wrong too. And we have this sort of alignment problem here manifested in the land of RL. So there was a group of Danish researchers who were building a program that could ride a virtual bicycle. And they were trying to get it to stay upright and ride to a goal destination. They started to add shaping rewards by incentivizing forward progress toward the goal, but they forgot to subtract progress away from the goal. And so instead of making the agent zoom towards the goal, what the agent did was in fact just ride very quickly in circles, racking up that progress reward 50% of the time. A similar thing happened to David Andre and Astro Teller, who were working on a robotic soccer tournament, and they decided to give their robotic soccer player this shaping reward for taking possession of the ball, because they thought that would kind of incentivize it to learn that it's good to have possession of the ball. Well, to their shock and horror, the behavior that resulted was just the program vibrating next to the ball, repeatedly taking possession of it and just racking up those points. So there's this whole area within reinforcement learning of how do you provide shaping rewards that don't create loopholes that your program can exploit. There's a lot of work being done to address this question, and we don't have time to get into all of it. There's imitation learning, which is sometimes known as behavior cloning or shadow mode, which is a very promising direction, particularly in self-driving cars, where you sort of put the reward objective to the side and you say, we're just going to treat this as a supervised learning problem to imitate the person. And we can talk more in the Q&A if you want about reasons that might be a good idea and reasons that might be a very bad idea. But I think for me, one of the most interesting areas here is the idea of learning the reward itself. So rather than having the humans put in the point system that they want to optimize, the system itself is going to learn that reward. And so this is the idea of inverse reinforcement learning, which might be familiar to some of you. One of the people who has been a real pioneer in this area is Peter Abiel, who's at Berkeley. And he's shown, in these kind of toy examples initially of driving a car, that it is in some ways easier for the system to model the reward that it thinks you're trying to optimize than it is to model your behavior directly. This has been used very dramatically to get helicopters to perform all sorts of wild stunts. But there is one drawback, which is that we can't always supply the demonstrations that we want our system to learn from. And so how might we teach a system what we like, what rewards we are kind of subconsciously motivated by, even when we can't actually demonstrate that behavior? This is one of my favorite papers in this space. This is the work of a team at OpenAI, including Paul Cristiano, and a team at DeepMind, including Jan Leike. They were asking this question of, can we build a model of what we think the human's reward is just by asking them a series of yes or no questions? And in particular, they had this idea. They wanted to teach a robot how to backflip. And I think this is a perfect example, because if you've got a virtual robot in this virtual, Mujoko environment, it's very, very, very difficult to actually specify in your mind, how do I want to operationalize the idea of a backflip, right? Which torques, which accelerations, which angular momentums do I want to reward? It's extremely, extremely difficult to figure out how to make that translation. On the other hand, it's very, very easy to see a backflip and say, yeah, that's a backflip. So what they did was they just showed pairs of videos of robots doing initially random things and saying, which of these looks slightly better to you? Which looks a little bit more like a backflip? And they would use that data to create this reward model of what the system thought a human thought a backflip looked like, what rewards it thought that were motivating the human's preferences. And what I think is so cool about this work is that after just 1 hour of choosing between video clips, left or right, which looks more like a backflip, this is the behavior you get, which is kind of this perfect gymnastic backflip. It's tucking the leg to speed up and increase its angular velocity. It's sticking the landing, all of which would just be extremely bewildering to try to actually specify in code. So for me, there's something really promising and really helpful here. I mean, there's obviously something precarious maybe or risky about treating even the reward as some kind of black box. But there's also something for me incredibly hopeful about their instructions to their Mechanical Turk reviewers were just look at the clips and select the one in which better things happen. I mean, it is the vaguest possible way of framing that problem. And there's something here for me very hopeful about, what values we might be able to communicate through a method like this. And I think one of the fundamental issues in data science and machine learning is that one is often kind of stuck dealing with the KPIs that you can instrument. There's kind of a tyranny of the measurable or tyranny of the operationalizable. And there's some hope, perhaps, that we are kind of beyond that we are starting to push into this territory where systems can learn from us, even the things that we can't fully articulate. So in conclusion, I think we've seen this undeniably abrupt, let's say, progress in the capacity of data science and ML systems. That progress has manifested both in what they can do and also in how broadly they're deployed in society. And that's provoked concern. That's provoked concern on a number of different fronts. But that concern has itself created, I think, one of the most exciting as well as important movements within science. I think it's one of the most essential, but also kind of invigorating areas in computer science, for me, in all of science, really. So I think whether you're persuaded or not by the long-term arguments about things like AI safety, existential risk, whether or not you're persuaded by that, you are likely facing the alignment problem, some version of the alignment problem, every day. And while there's no simple prescription, no one size fits all response to that, there is this growing community, this growing arsenal of tools. And I think all sides of this community, present and long term, ethics focused and safety focused, theory and practice, academia and industry, have something to learn and also something to teach. I think the alignment problem is an old problem, but it is becoming urgent and it's becoming acute, and it's not going anywhere. And I would also argue that it has something profound to teach us about ourselves along the way. And here my mind goes back to 1952, when Alan Turing was part of this BBC radio panel talking about artificial intelligence. And he was describing these very early experiments that he was doing and trying to do what we would now call machine learning. And he was talking about, it's extremely painstaking. There's a lot of manual intervention. I was always having to tweak things and adjust things. And one of his panelists interrupts him and says, "Well, Turing, who was learning, you or the machine?" And Turing responds, "Well, I suppose we both were." So I'll leave it there, and I look forward to your questions. Thank you very much.
I feel like normally this is where I'd be walking back onto the stage to applause everywhere, Brian. So yeah, you'll have to imagine that. It probably won't be the same effect of me just sat here clapping. But mate, thank you very much. I really, really did enjoy that talk. And yeah, we've got a number of questions that I'd like to get into and discuss with you, if that's okay.
Absolutely, yeah, I'm looking forward to that.
Perfect. Just briefly before I do have to give a quick shout out to our sponsors at this point in time. Obviously, the Data Science Festival, we're a grassroots community, and we do manage to keep all of our events free, thanks to the forward-thinking support of companies like Facebook, ASOS, Depop, Dataiku, Royal Mail, Deliveroo, Gusto, and of course, Data Idols. So thanks to all those guys for supporting the community. In terms of some questions, Brian, I think the first one I'd like to kick off about or off with is that you were talking about fairness, the fairness, bias, and ethics community, and the long-term AI safety risk community, needing to come together, need to be more connected. Do you think these two communities are quite separate at times? And how do you see things going from that perspective?
I think that's a really interesting question. Yeah, when I started working on the book, part of what motivated me was that I had this hunch that I was seeing the work that was beginning at that point to happen around fairness, bias, transparency, and I was seeing, out of the corner of my other eye, this work that was starting to happen around safety. How do we sort of infer these human values, et cetera? And it did start to feel to me that this was one broad movement, whether you're focused on the near term or the long term. It is the same question of, are the systems doing what we want them to be doing? Are we able to translate our intent into that actual objective? And it has been interesting for me over the last 4 years. Initially, it was pretty polarizing when I would mention this to people. Some people would push back. Other people would say, "You know what? I think you're exactly right, and I think that is kind of underappreciated." More and more, I'm seeing people coming around to this idea that people in technical AI safety feel like there's something they can take from the near-term community. And we're also starting to see collaborations now happening across that gap. So just recently, there was a paper that came out of the Partnership on AI. It was a collaboration between Jonathan Stray, was kind of well known before that for working on the criminal justice fairness stuff, and Dylan Hadfield Manel, who's now at MIT, who's thinking about kind of human reward modeling, AI safety, things of that nature. And they're kind of putting their heads together on this question of what does it mean to make ethical recommender systems? And to make a recommender system, you might want to take into account not just this immediate thing of the clicks or engagement in a short-term sense, but longer-term questions of is the person later going to be retroactively satisfied with the experience they had and so forth. And a lot of these harder to capture things. And I think those ideas are starting to come out of the long-term safety community and actually get used in practice. So to me, that's just the beginning, but I think it's really exciting to see the sparks start to jump across those two communities.
Yeah, I think it definitely has to happen as well, isn't it? Going back 5-10 years, technologists just were focused on solving problems and building systems. And then now it's quite clear with the data we have and what they're being used for, there could be untold consequences down the line, can't there? So as scientists and developers, we have to be aware of that situation as well, don't we? So very interesting, definitely. And we've got a question that's coming from Eva. Eva is bringing up it's something that you talk about in the book, actually, so definitely very keen to get your take on it. Eva was asking, what are your thoughts on the usage of algorithms to filter CVs for a job position? Do you think that they can accidentally contribute to opportunity gap or give unfair advantages to people that understand how the algorithms work? Can it be improved?
That's a terrific question. So yeah, we talked in the talk, we touched on supervised learning and reinforcement learning. We didn't talk about unsupervised learning, which is where a lot of these language models come into play. And we've absolutely seen these questions of language models picking up things that the team building it would rather they didn't. And there's an example I give in the book of a team at Amazon that's putting together a system to rate job applicants on a scale of 1 to 5 stars. So ironically, rating prospective Amazon employees the same way that Amazon customers rate Amazon products. And it's doing it in part based on this word embedding vector model. And as they were auditing the system, they started to notice that this model was penalizing people for using the word women's in their resume. So they got rid of that. And they later found it was penalizing people for talking about having played kind of female sports like field hockey, for example, in the US. They were able to get rid of that. And ultimately, they found it was rewarding not just these specific terms, but kind of general patterns of speech. So certain kind of quote unquote masculine ways of talking about business, like we executed a plan, we captured market share, these kind of militarized terms of speech, were all being rewarded by the model. And ultimately, they just concluded that they couldn't be confident that they had found everything that was kind of off about it. So they just scrapped the project entirely. So I think there's a lot of scrutiny that needs to happen in that space. There's some interesting work being done. People at Google like Tolga Balukbasi on can you identify in this vector space kind of subcomponents of gender that reflect stereotypes as opposed to other more kind of essential attributes? And can you just identify those vectors and delete them? It turns out to be a pretty complicated story, and sometimes the things that you think are going to help end up hurting. So there's no clear answer, but it's a really active research area. And I think particularly as we are now even moving from these word embedding models to giant transformer networks, right? Like GPT-3, which has, 175 billion parameters. These questions of how do you even measure, let alone try to correct for some of those things, are only getting harder. So I think there's a lot of work happening. It's very exciting, but can't happen soon enough.
Absolutely, yeah. It's one of those. As some of the models are that complex, you can't even necessarily understand why it's doing some of the things it's doing. I'm going to shoot straight on. We've actually got quite a few questions coming in now, so I'm going to do my best, everybody, to get through as many as we can in the time that we've got. The next question we have here is from Marco. It's not something, if I'm honest, that I've come across, so hopefully it means something to you, Brian. If not, obviously we can move on. So Marco is asking, what's your view from the so-called nudge units being used by governments? They use data and models to act on behavioural change of the population. Do you think that this can be dangerous?
That's interesting. So by that question, I take this idea of there are a lot of ways to frame a decision in order to kind of affect how people will decide. And there's a famous example of, if you make organ donation opt in, then you get like 20% of people opt in. But if you make it opt out, then only 20% of people opt out. And so you get quadruple the number of organ donors, but then you get into these ethical questions of, have you coerced people by framing the question in a different way? A lot of that work I think is really interesting. And the ethical questions around what constitutes manipulation, what doesn't. I think that is a critical conversation that needs to happen, particularly in social media. I don't necessarily think it's objectionable per se, in the sense that it's unavoidable, right? You have to frame the question some way, and there is, in my view, no neutral way to frame a lot of these things. But I do think that a starting point, and this is not the end of the conversation by any means, but I think a starting point is transparency. If you tell people, for example, in a news feed or something like this, if you're able to kind of expose, this is what we're optimizing for, and perhaps even give the user some kind of leverage. The user can say, actually, I would like to optimize for something slightly different. These are my goals. That feels like a starting point, but I think this is, a fundamental question.
Perfect. Thank you very much, Brian. Talking of transparency, that actually leads us on to what looks like a simple question from Nelly, but there's probably going to be a very deep answer to it, actually. But Nelly was asking that, do you think that open source can help for more transparency in AI?
I certainly think it has a role to play. I think it's maybe necessary but not sufficient. In some ways, it can cause harm. So, for example, a lot of what we've seen in facial recognition and things like that is, a certain group will create a data set in whatever year with using whatever methodology to support whatever kind of research they're trying to do. And this paper becomes highly cited, or maybe they put the data set online. And this then just other groups, it's so much easier to just grab that data set, or to even grab a trained model and then fine tune it for something else. And that can be a means by which some of these bias problems creep in. You get a data set that was designed for one application, you start using it for something else, or just the way that these models kind of live on. You're grabbing some code that might be 15 years old at this point. So it's, I think transparency is critical. I think we're really lucky to live in a culture of transparency where, even these groups like DeepMind, that's part of Google, is just freely sharing a lot of their research, particularly their safety research. And OpenAI, who's their kind of ostensible rival in some sense, at least friendly academic rival, is doing the same thing, and they're collaborating with each other. And so that, I think we should be really grateful for that culture of openness. And I think that's something that we should certainly want to continue.
Fantastic. I'm going to jump onto a question from Mohammed. Mohammed was basically asking, since human beings are, stereotypes by nature, how bad or good is the teaching of computer to be stereotypes, or is the concern present and applicable only when the stereotype is a byproduct of the labeling of the data? Is it the data that's racist, or is it that we're teaching the program to be racist?
In a lot of cases, I think the model is merely reflecting something that exists in society. And so there have been some really interesting papers on language models in particular. I'm thinking there was a group, interdisciplinary group at Stanford and one group at Princeton, showing that if you look at the gender dimension within the word embedding for names, Stacy, Hugo, whatever, those, and you normalize this gender dimension, it tracks almost perfectly the actual census data of what percentage of the people have that name are of either sex. And likewise, there's been some research showing that the gender dimension of professions like secretary, linebacker, whatever, almost perfectly correlates with the percentage of people in society that have that profession. And what's really fascinating about this is that you can look not only at the present day, but you can take kind of historical tranches of data. Like let's take a corpus of newspapers from 1910, 1920, 1930, and you can use the embeddings to actually watch society itself change. And so I think, one of the things that's encouraging here is that we're really at the beginning of this golden era, I think, of computational social science. So not only do social scientists, have the ability to use machine learning to measure things, but they can actually use the products of those machine learning models, the actual embeddings, the representations, as the object of sociological, anthropological study. And so it's a way of holding a mirror up to ourselves in some ways, for better or worse. And I think, you could imagine almost a real-time dashboard, that's continually scraping text from the news, from the internet, whatever you want to say, and just showing you, like, are we 0.1% less sexist or more sexist than we were last week? The idea that we could actually sort of dashboard the culture is fascinating, and maybe the mere fact of exposing it will sort of point us in the right direction. But it's a big question, obviously.
There's some good to be had there, hopefully. We're going to go on to a question from Tarek. He's managed to squeeze it across two questions, but I'll do my best to put it together in one. He was making a good point, actually, and he was saying that many businesses and organizations might not necessarily have the expertise to understand the nuances of what you're talking about in terms of some of these problems that we could be coming up against. And essentially what he was asking is, what is the simplest advice you can give to organizations in that area? Is it around testing? What should they be looking out for? How should it be approached?
That's a great question. I mean, we're starting to see kind of a consultancy market for groups. I'm thinking Kathy O'Neill is one person who's been active in this space. I know some other folks around the Bay Area that are kind of starting nonprofits that can advise, right? So maybe your organization is small enough where you don't have a dedicated team thinking about these things, but you might be able to bring someone in to do a kind of fairness audit or a bias audit or something like that. So I think that's one way. But in many ways, I think just a little bit of awareness goes a long way. So, if I've succeeded in the last 30 minutes and, haunting you with some of these stories of things gone wrong, then that gives you a way to kind of pattern match something in your own experience. I think that's a starting point.
That's it. We've started the conversation right here. It's happening. So I'm a little bit conscious of your time, Brian. We've got two more questions. Hopefully we can fire through them. So the first one's from Peter. So if I'm honest, it's a little bit of a broad question. It's getting your take on what the future looks like. He's talking essentially like a lot of this stuff that we're doing around algorithms, machine learning. It's going to change society. It will potentially lose jobs or change what people do with their lives and stuff like that. How do you see society restructuring in the longer term? Is it a danger? Do you see the positive there? What are your thoughts on the future?
Yeah, I mean, I think there is an aspect to the alignment problem. I was talking with a Google researcher, and they were expressing, a little bit of reservation about the term alignment problem. They were arguing, shouldn't it be something like the value communication problem? Because it's really a matter of like, how does the human get what's in their head into the system? And I think there's some truth to that, but I think it is more than communication, because alignment, I mean, even the term alignment that we now use in machine learning is kind of borrowed from the business literature and saying, like, are people's incentives compatible? Are your employees incentivized to do what you want? Are these two partners in a contract incentivized to actually help one another? And those problems are bigger than machine learning, certainly. I mean, these are age-old problems. And for any machine learning system, you can ask not only what is the objective function of that system, but zoom out. What is the objective of that team? That team wants to has any number of goals, including their performance review and certain KPIs that matter to their manager, who has pressures from their manager, and so forth. And that's an alignment problem too. I mean, every company has to think about that internally, but I think there's also broadly this question of, are the business models compatible with what we as users want? That's an alignment problem. I think for me, my pessimism exists more around that than around the actual scientific technical part. I think if the last 5 years are any guide, we have a lot more reason to feel upbeat about the purely technical aspect. But we've been thinking about the problem of like governance in society for millennia, and that's an age-old problem. I think one thing you could argue is that if you think about something like climate change, you could think of climate change as a kind of alignment problem, that we've operationalized these criteria like GDP per capita or quarterly shareholder returns, et cetera, that generally correlate to the other stuff that we care about. The same way that scoring a lot of points in the boat race game generally correlated with winning the race, but not always. And so we're now getting to this regime where we're learning, oh, well, here are the values that don't correlate with that beyond a certain point. And I use the metaphor of overfitting, right? We're essentially overfitting on these particular metrics, and it's starting to kind of mess up all of these other things that we cared about that weren't explicitly captured in that. And to the extent that technical AI safety research and a lot of this work that I was talking about at the very end is about, capturing the broad set of things we care about without forcing us to narrowly define some actual operational criterion, could we scale that up to society more broadly? I'd like to think so, but that's a big task. So I think that will be essentially the defining task for humankind for the next couple decades.
Feels quite big. That feels quite big. Mate, I'm going to finish up the very final question. And I mean, you talked about the research happening around the alignment problem, and you kind of alluded to the fact that it also teaches us something about ourselves as people. I found that quite intriguing. Is there anything, just to finish, that you can elaborate on from that side of things?
Yeah, I mean, I really do think that this is a process that is not only a problem to be confronted and solved, but it's also there's a really profound opportunity for self-discovery, and I mean that in a number of ways. I think if you think about this idea of rewards, right? What's the reward function that you want to administer to the agent to incentivize the behavior that you want to see? That's bigger than robotics. It's bigger than news feeds. That's the question of, as I said, corporate incentives. How do I get this team motivated to do the things that I want? It's the problem of parenting. And I include a bunch of examples in the book of parents, many of whom are also computer scientists, kind of facing alignment problems in their own home. One is Princeton professor, cognitive scientist Tom Griffiths, who gave his youngest daughter, a lot of praise after she swept up a bunch of dirt that was on the floor. And while she was beaming at him, she dumped all the dirt back out onto the floor so that she could clean it up again and get a second helping of praise. And that is a canonical kind of reward cycle problem that people in AI would recognize. So broadly, I think as the project of artificial intelligence progresses, these systems in a way become ever more and more recognizable. And in the book, I touch on a lot of these connections. There's this very, very deep connection between what's called temporal difference learning, which is this RL technique, and the dopamine system in the brain. In fact, it was the reinforcement learning community that figured out how to make sense of all this really confusing dopamine data that the neuroscientists were wondering about. So we're now at a point where AI is kind of solving some of these riddles in neuroscience. We also touched very briefly on this idea of sparse rewards, of how do you motivate an agent to get the right idea, even if the actual reward is really far away. And this is an area where computer scientists are borrowing directly from the infant psychology community for things like formal models of curiosity and play, and intrinsic motivation. And so there's a lot of these fronts on which, not only are we holding a mirror up to ourselves culturally, right? Language models are showing us this kind of unflinching view of everything in our culture, good and bad. Reinforcement learning is teaching us something about the fundamental mechanisms of not merely just these good engineering tricks that can play Go and solve video games and stuff, but fundamental mechanisms of learning, reinforcement, reward, some of the same things that evolution discovered that are operating in humans and animals. And so for me, there is something very, very profound underneath all of this, which is this confrontation with the nature of society. How do we structure, the things that motivate people, of parenting, and of the mind itself. So there's a lot we have to get right, and it feels like a bit of a tight wire act, but it is also at the same time, I think, that one of the most incredible frontiers of scientific discovery too. And so there's something really kind of joyful about that as well.
Fantastic. That's a very positive note to end on. So thank you very much for your time today, Brian.
It's my pleasure.
Really, really enjoyed it. I'm just going to wrap up by saying there's one question coming there from Eva. Brian's written multiple books. Which one do you recommend we pick up first, the new one? What I'd say is all of Brian's book have been very enjoyable. I'm halfway through his current book, The Alignment Problem. You can tell that you've spent 4 years on this, actually. It's very, very thorough, but it reads with a lot of real life relationships and stories mixed into it. And I must admit, I'm flying through it. So I definitely do recommend the book to anybody that is watching today. So I'm just going to wrap up one final time. Thank you very much, Brian. Hopefully we get some point where you're in the UK in the future and we can revisit this in a live environment.
It would be a pleasure. I'd love that.
Perfect. Well, enjoy the rest of your day. And
thanks
again.
so much.
Cheers. Bye-bye.
Bye.